laws, they go by a few different things, and the reason we have to add some extra ways or a method to try to solve circuits, because so far we're like, oh, we can find voltage, current, and resistance everywhere. Ms. Jones taught me. We just simplify a circuit, and then I have one unknown. I can use it to find another unknown, just kind of whatever. We're going to get to a point, we're going to see problems where you can't do it. You're going to have, there's too many unknowns, and we're going to have a strategy to solve. And that's what this whole thing is about. All right? So, the first law, it's going to start nice and simple with cute little pictures. Okay? And we're going to all think it's easy. Okay. And it is until you get to the problem that you can't solve. Okay. All right. So it's sometimes called I think officially it's the current law, but a lot of people call it the junction rules, the junction rule. And so I use both. And again, a lot of videos, and it makes sense to call it the junction rule because it occurs at a junction, and so it's easy to remember. Okay. And it says the sum of all, you already know this stuff. I already been teaching Kirchoff's laws without using the word Kirchoff. So it says that the sum of all currents flowing into a node equals the sum of the currents flowing out. Right? In equals out. We've been doing that already. All right? And here's the fancy way to write it in case, in equals out. Everything going into some kind of a junction where there's an intersection of wires that run together, whatever in, the same amount of current has to go out. There's nothing else to say. So, let's try it. So right here, can you reason through what's happening here?
4.
Okay.
4.
Look at, we're 100% success here already. All right, so here we can think, I'll just play through what should happen. Here's 5 coming in, and we know 2 is leaving. So what's this leaving?
3.
This would have to be 3. We have 3 entering this, and we have 1 entering it. So this leaving must be 4.
The lights turned on that.
Okay, all right.
I want to do that in my head.
Yeah, you could have done it different, but that's how I'm thinking stepwise with Kirchoff's law. This one, a little more annoying. And yes, I just stole these images from, they're just Google image and some other site. But this bothers me. So does this bother you too? The -2 going this way?
No.
You know what it really is then?
Choose one, that one.
So just do that. If that helps you, it helps me. All right. And so what do we got now? So look at how much total is going in. How much total's in? 3, 4. Okay. 8's in.
8.
And 2's out. So what is this?
-6.
Okay. Ta-da! You guys are geniuses. All right. I'm going to give you a minute.
What?
How about this one? Oh, let everyone look at it just for a minute, and then we're going to let Mark guess. Does everyone have a guess?
Not yet.
Okay, let you evaluate. It's like Sudoku stuff, isn't it? Again, very much. Right? It's all problem solving. It's a simple rule that you apply. All right, what do you got, Mark?
0.
0. Did we get 0?
Yes.
No.
Let's go.
No?
No.
No? Let's evaluate it again. What's going on? Look, I got 4 this way, 4 in, and 6 out. If there's 4 in and 6 out, what is this?
-2.
Let's not use it. Let's
2 to the left.
Okay. We got 2 this way, right? So now, if we have this, let's evaluate this. Well, do we need to evaluate this? Oh yeah, because that's there. Sorry, I went too far. How about this one? We really have 1 this way, right?
Yep.
And we have 3 this way. So we have 3 in and 1 out, which means this has to be 2. And if 2 is in and 2 is out, what can this be?
0.
0, because it can't be anything else. Okay, you see how it's, okay, fun. All right, now we're all trained in that rule. Now we have one more. Kirchoff has the voltage law. All right, so the voltage law is also known as the loop rule. Okay, I wonder why. All right, because we'll make a loop. So Kirchoff says the sum of the voltages around a loop is 0. Okay, we can write it like this: the sum of voltages. All right, where n counts the element voltages around the loop, so every little voltage that you have. And you think normally, so you think there might be just one thing that's voltage, like the battery, but we have more things, right? The battery has voltage, but doesn't every device have a voltage drop? So if we add everything that has voltage around the loop, it should add to 0, okay? Here are our little rules for this. You can trace a loop starting from any point. This is where it's a little troubling having everyone do a complex problem, because if everyone starts at a different place, everyone has their own way, then it's really hard to look at everyone's steps, because everyone can start off differently but end up at the same answer. Okay? All right. So you can make in any of our, so far we've only done, no, we have, whenever you have parallel, you have multiple loops, right? Okay. So we can go around and end up back at a starting point. The sum of the voltage should equal 0. Okay? You can go clockwise or counterclockwise. I tend to be a clockwise person, but it just depends on the situation in the picture. Okay? If a circuit has multiple loops, it's true for every loop. You could do inner loops, you can do outer loops, you could go backwards loops, you can do loop-to-loops, you can do whatever you want. Okay, so let's just look at a basic setup, all right? Oh, you know what I like to compare this to? Because we do lots of times, since voltage is potential, right? Electric potential. Then, or electric potential difference, really, voltage, right? And volts are just a position. And voltage is the difference from one position to the other position, right? And we need that electric potential difference to make things move, right? Well, we did this analogy before. What about if you are, let's say you're going for a run, okay? And you're gonna run at Peach Mountain, all right? And you're going up and down in elevation. You run whatever your path, your loop is, and you come back to where you started, okay? Tell me about the change in your elevation. Tell me about your elevation. 0. As much as you went up, you went back down, right? There isn't an easier way to go. Like, oh, it's all downhill if I went clockwise. What? You know what I mean? If you get back to your starting point, no matter what you do, right, you arrive back to where you started. And so that's in the same sense with the voltage rule. All your ups and downs, because voltage is different, all the ups and downs have to add to 0. You arrive back to where you started, okay? All right, so here is a simple circuit, and we're going to look at it. And we're going to do the loop. We're going to do loop to loop. And I've laid out underneath what's creating our voltages here. So we have, oh, and I gave positions. We do this a lot here, so everyone knows where we're at. So A, B, what happened to C? C's gone. I may be, I don't know. I think I took off some of the stuff in this picture. It's okay. So A, B, there's maybe C was here at one point. I don't know. All right, so we're going around like this. All right, and we have first a voltage there. All right, and so we're going to go clockwise. Oh, other things. I already found in this circuit to make so that we can do some easy steps here. That add up all of these are in series, right? So it's 1,000, okay? If it's 1,000 and this is 20 volts, if I take 20 divided by 1,000, I get 0.02, okay? So I know I have 0.02 amps. Where do I have 0.02 amps? Everywhere. Okay, good. All right, so we have 0.02 amps everywhere in this picture. and I want to figure out my volts everywhere. Okay, so when I go from A to B, I'm going to go from the negative part of the battery to the positive part of the battery. I know batteries, we're used to seeing long line, short line. You can also see this. So anyways, so negative to positive part of the battery. Do you remember our old saying, the positive plate is the plate of higher potential? The mantra? We got to keep that. So if we go this way, what kind of voltage change do you have? Positive. You're going uphill. Think, you know what I like to think of it like, for like potential energy, you just are climbing the hill of a roller coaster so that you can go down. This is inside, Josh, maybe if you think about this is inside the battery, so this got you uphill, and now what do you get to do? You go, woo, we get to run down.
But do you go up again?
Not in this one.
Oh, there's an arrow.
Oh, at the end. What?
Never mind.
It's okay. And the more complex ones, yes, there's multiple hills in our roller coaster. Okay. All right. So from here to here, that's a positive voltage change. Okay. All right. Okay. So negative to positive, this is something to know, and I reiterate on the next page. We get a voltage gain. Now, when we cross a resistor in the direction of labeled current, all right, we get a voltage drop. Remember, I've already mentioned this. Like, what is, what is the voltage across? And this will be a voltage drop. So now, how much voltage from here to here? Okay. Do I have to, are you serious? Oh, that's on video forever. Okay. All right.
Grady.
Bye. I got lost. Okay, so remember, I want V here. How am I going to find V here? V equals IR. Don't I know the I, 0.02, and my R is 100? Okay, so that would give me 2 volts, but it's a drop. It's negative. Okay? And can we figure out what the next one's going to be?
4.
All right, and the next one?
3. Oh, oops.
That's okay. That's all right, because we're times 2 at 0.02. And then the last one? And look it! Kirchoff was right. All right? So this gives you your positive, and then all of these are negative voltages, and it equals 0. Okay? Cool. All right. I'm going to have, now, we're going to arm ourselves with steps, what we're going to do, and then we have to do a problem. I used to do this with stoichiometry. Did you ever learn stoichiometry in chemistry class? And people it seems like this crazy, too much stuff. And I always had a sheet with do this first, and then you're set up and you'll be okay. But while you're going through the rules, you may not understand why we need to have these, but we're going to write these rules down or look at these rules, and then we're going to do it to a sample problem where we need to use Kirchoff's laws. Okay. All right. So the first thing, when we get this circuit we need to analyze, we have to label the current. We have to label the current. We're going to label them with I's. I1, I2, and I3. Now this should scare you, right? What does that tell you? Are you just going to have one series circuit loop? No, because you'd only have I1, and we would not need Kirchoff's laws. But we will need Kirchoff's laws because we'll probably have I1, I2, and I3 for each segment between junctions. This makes people crazy. We choose the direction, the arrow we make, doesn't matter what direction. We saw that pretty much in one of our sample problems. If you have a current arrow in one direction and it's not the way the current's really flowing, what happens to the I? The I will be just negative, right? And if it is in that direction of the arrow, it'll have you'll end up with a positive I. We like to try to pick a little less than arbitrary when we draw in our arrows so that it ends up the right way, but it doesn't matter. It mathematically will fix itself, okay? All right, but you have to label each of the loops with a direction. Draw in an arrow and then label them, okay? Then we have to identify our unknowns. This is like math class. You need as many independent equations as unknowns, okay? As we just saw we can do, we can use V equals IR for each resistor. So that if we don't have V, we do an I times R, and sometimes that we don't know an I, so it's just part of the equation. You'll see in a minute, all right? Then we apply Kirchoff's current law or junction rule at one or more places, depending on how many of those equations you want. Normally, you only need one of those, and then you apply Kirchoff's voltage or loop rule for one or more loops. Normally, it is more than one loop that we're gonna do. Follow the loop in one direction only, and it's going to do it in the direction you chose your current. Okay? All right. And as I stated already, but I'm restating it here, for a resistor, we apply Ohm's law, V equals IR, and the voltage or potential difference is negative if your chosen loop direction is the same as your chosen current direction. So if you're going around a loop, and you're matched with your arrow for your current, then it's going to be negative. If you are swimming upstream, it's going to be positive, okay? And again, we're going to see with an example. All right, we said this already. This is so everything's on one piece of paper. For a battery, the potential difference is positive if the loop direction is from negative to positive terminal, okay? If you're going from across a battery from negative to positive, it's positive. That's it. All right. This sample problem I'm doing has a separate YouTube video. If you don't like my explanation of this, although I'm pretty much copying what the guy did for this one, but you can already see it, or my video quality is bad. All right? Okay. All right. Let's all look at this and see that's a little more complicated than the one we just saw, right? What's the problem with this? We've never seen this so far.
3 batteries.
There are 3 batteries. What the heck? Right? Oh. And look at how those batteries are. Are they helpful? Look at this battery. Then look at this one. They're fighting each other. Yeah.
When would this actually exist?
I don't know.
Who would do
When
that?
would this really exist? I don't know if this is just to torture physics students. I don't know. Don't.
Wait, how are they fighting?
Would you even be able to?
What do you mean they're? Because here they're connected. So which way is the current going to go?
Silly.
Okay, so we can, but you see they are fighting each other because, right? If you say current's supposed to, conventional current leaves this side, then it'd want to leave this side. Okay, all right. So you see there's lots of complication. Do you see that with what I've taught you last lecture, you couldn't solve this? There's too many things that we don't know. Okay, I know you are really smart. You could do it. Okay, so here's what we're going to do. I1, I2, I3 direction. It says it was chosen. It wasn't. We're going to choose it right now. So I'm going to do that. I'm going to do it in blue because that's what it is on my other paper. Okay, so I'm going to do what Josh was saying. I said, well, where's it going to go? Which way is it going to go, Josh? Okay, this is more powerful than this one. So we're going to say, think that's probably what's going to happen in the end. So let's choose this. I'm going to draw that, and that's my I1, just making sure. I'm going to keep referring, because any little mistake will mess this up, and it will be sad. Okay, all right, so now we have that direction. And where does doesn't that go all the way to this junction right here? And wouldn't it have to keep going this way too, right? Okay, it depends on how far you want to draw that, but you could keep saying, right? If you want I1, you can just keep labeling it everywhere. Okay, I'm going to call this one I2. Now, I'm just going to call it this way, just 'cause. Okay, Now again, some people might not like it because I1 is gonna run into I2, right? But that's, can happen, right? Okay. Right? And if they do, it would make sense that this goes this way, right? So it's just picked. You could choose whatever you want. If you don't like that, you say, I want to make that one go that way. Sure, do it. Okay? And when you mathematically solve it, it would give you a negative then. It's okay. Doesn't matter. All right. Are we good on this step? All we did was label. Okay. Now, how many unknowns do we have? 3. Okay? And so we need 3 equations. We know we need at least 3 equations. So let's do the first one. And oh, surprise, I gave it to you already. But could you figure this out? Could you figure this out? Can you see that from this, if we look at this, that I1, this is your out, I1 and I2 are out, and it must equal I3 in. There's only 1 in and 2 out. Don't they have to equal each other? Yeah? I3 coming in has to be split into these 2. Yeah? So I3 equals I1 plus I2. We okay? Okay. Check 1 equation. We need 2 more equations or we can't solve this. So, now here's trouble because I don't have enough screen to have everything up on the board. I know. My picture, I didn't think about that. But I can. No, you can't. Okay, that fixes a lot. Okay, good. Okay, I planned that. All right, so here is my voltage loop rule for loop ABCDA. Where's ABCDA? A, B, C, D, A. Right? And let me relabel this. I1, I2, okay, and I3. Okay. So, here are my parts. These are all the things that have voltage. I have voltage from V from A to B, right? There's the battery. B to C, there's a resistor. C to D, there's another battery. And then D to A, right? There's another resistor, okay? So, let's establish it. Let's put some numbers in place, okay? So, what about VAB?
20.
What should I write? Positive or negative?
Positive.
We're going this way around the loop. It's going from negative to positive, so it's positive. So we write plus 20, okay? All right, now what about VBC? Okay, so for VBC, we're gonna now apply V equals IR, okay? And we don't know I, but so it's gonna be I1, isn't it? And our R is luckily nice small numbers, 2 ohms. Now, we would normally write, I'm just gonna write it here, so you would have I1 times R, and my R is 2. But we like to write it in a little bit more, like looks like math. And with math, what do we normally do? We put the coefficient first. So let's do that. Now, what about sign? Is it positive or negative?
Negative.
The rule is, if your loop and your current are in the same direction, then it's going to be negative. So we have a negative 2I1, right? Okay, all right. So we've traveled here, now we're traveling here, and we're going this way. So tell me what I need to write here.
Negative.
Negative 10. You with me? Right? Okay. Because unlike this one went from the negative to the plus, this one is going plus to minus. Yes? Okay. All right. Do this part real slow. If you have one sign wrong, do you understand? There's a lot of math. We have If you do that, you get one sign wrong, everything is wrong, you have to start all over again. It's bad. Okay, all right, so now what? Here to here, we have 4 ohms, all right? And so I know I'm gonna have a 4 times I1. Is this positive or negative?
Is that I2?
Oh, Lordy. I'm sorry, I was so stuck. I2, and the sign, we are going this way upstream, positive. Okay? Equals 0. Sweet. All right. Now, we can rearrange this formula. Okay? Can we put some stuff together? I guess we can do that right now. This will be our base equation, but we've got to, can we put these two together? Right? So we have 10. All right? And I have it written, I'm going to rearrange this so it solves for I2. Just cause, okay? It's going to help us later.
I mean, why not call I1 why not call I1 negative? Because we are going from the plus to the minus terminal.
Why call I1 negative?
Positive. We're calling it positive.
We're not calling I1 anything.
I mean, oh my God. Voltage AB.
It is positive. Voltage AB is positive.
Why aren't we calling it negative? Because you could say, okay, it's going from the positive.
No, because we have a set of rules and we can't change the rules. It's not going to work, okay? We have established these things belong together, all right? That if we go from the negative to the positive, we're calling it positive, all right? Otherwise, we have to flip the resistor, which everything, you could switch change. We'd multiply this whole equation by -1, but we're not going to. Yeah, I mean, in terms of that, but whatever. So we're just moving things around. So we're going to solve. I'm going to get this alone. So I'm going to write 4I2 equals 2I1 minus 10. Okay? All right. So actually, let's do it one more step. Let's just solve for I2. So I2 equals, right? We're going to divide everything by 4. So that makes this a half, right? I'm going to leave it because the video I watched left it, and just, I know you guys like numbers a little bit better like this. So I'm going to leave it like this for now. We'll later turn them into decimals. Some people, if you're a pure mathematician, right, you keep those fractions everywhere. I keep fractions until they annoy me, and then I divide them out, okay? Because our answers are always going to have some significant figures anyways. It's not pure, although you could, are you arguing this is pure numbers, or are we going to argue that we have 2 or 3 significant digits? I don't know, okay? All right, do I have that? So, bing, bing. Look what we got. We have equation number 2. We have to do.
I didn't like that. Felt like Big Bang.
No, we're stick with me. I know, you do what you want. You could do whatever. There are 100 different ways you could end up solving. So you will, and if your mind works different, in the end, we will all be back together. All right, now we're going to change our loop. All right, so now, well, let me just change my color. So we're going to do, must be a little different. What color? I'll do black. All right, so we're going to do loop ADEFA. Okay, we're going this way. We're starting here. Okay? All right. Right? Just making sure. Okay, now what? So here are our parts. We have that resistor. Look what we have here. Nothing. Yeah, we get out of one thing. Then we have a battery and another resistor. So there's only 3 things here. Okay? All right. Good. So tell me about that one. What are we going to have?
Negative.
Is it positive or negative? Negative because the loop arrow and the current are in the same direction. So we have negative 4 I2. Okay? Now what? I write it every time just because I'm going to screw it up. Negative to positive
Plus 30.
plus 30. Okay? Then up here, my I arrow and my loop arrow are in the same direction.
Minus 5.
Minus 5. What loop? What? Oh, look what we got now. I3. Yeah? Equals 0.
Wait, aren't you also missing VDE?
There's nothing there.
There's nothing there.
We talked about it while you were working out the problem.
Okay.
Yeah, there's nothing there. The wire, we're assuming the wire has no resistance. Yeah? Yeah. Okay. So what do I want to do to this equation? I want to solve this one for I3, just because I have, some prior knowledge. All right? So I'm going to boot that stuff to the other side. All right? Yeah, that's all I'm going to do right now. So I'm going to do, 5I3 equals, throw that on the other side, and then I'm going to change the sign so that we don't have a negative. So it's going to be 30 minus 4I2. Okay? And I'm just going to leave it like that for right now because we're going to substitute things in later anyways. Okay. You know what we do now?
Systems of equations.
Yeah, it's math. So this is, and I should have, okay. So I'm moving this, I'm going to move this way up.
No, it would be so
Oh, no.
No.
It won't let me. Oh, Lordy. Well, I'm just kicking this out of the way.
No,
Okay.
if you're watching the video, we wish you were here.
All right. So let me rewrite those equations at the top so that we get established here. So we have I3 equals I1 plus I2. Then we had I2 equals I1 over 2 minus 5 over 2. Okay? Then we had 5I3 equals 30 minus 4I2. Okay. You could do this however you want. I'm going to do like was in the video, but you could do whatever. So here's what I got going. Forget which one I did first.
Jones.
Oh, did I do something? What?
No, I just wish you would know which one you did first.
Well, there's a lot of stuff on my paper, and I already forgot. Okay, I think, we're going to do this one first. So we're going to take this guy. Nope, hold on. Nope, let's just do this one. We're going to go like this, and we're going to put it in right there.
Okay. Slay.
Okay. All right. So if we do that, what are we going to get? We're going to get a mess. So 5I3 equals 30 minus, right, 4I1 over 2 minus 5 over 2.
That's fine though.
Okay. Yeah, you're used to all this stuff, right?
Yeah, I like this.
Okay, so what are we going to get? We're going to get, you see that becomes 2I1.
Yes.
And then we have 20 over 2, which is 10. Oh, negative, pop. That's where you could just screw it all up from there. Okay, now let's solve for I3. So we're going to divide by 5.
8 minus 5 halves.
Oh, I got to put those two together. That's 40. Let's just put those together. Or do you want to do it, whatever?
I put them together. Just do it in your head.
Yeah, I'm going to do it in my head. That's 40 divided by 5 is 8. And then I'm going to have 2 over 5, annoyingly, again, right, I1. Okay? All right. So I have I3 in terms of I1, and I'm going to keep trying to do that. And I have I2 in terms of I1, okay? And now we get to have some more fun. Now, look what we're going to do. See I3? La, 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 la. Yeah. 8 equals 2, whoa, no,
What?
no, 8 minus 2/5 I1, right, equals I1 plus la 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 I1 over 2 minus 5. And you have to write clear enough that you don't screw up your numbers and letters, all right? Okay. Can we do this? I think we're there. I think we can do this. So at this point, I hate fractions. And I say, ban all fractions. So I'm going to say, I can't do it. I have to do this because your teacher's not smart enough. Okay? Now collect like terms, please. Okay? Did I do?
No, Julie
What?
she was changing it to death.
I just changed two. I don't like
I
it.
didn't see the point.
Oh, I'm
I
sorry.
got
I
really
never.
confused.
It's so bad. Okay, here. There we go. Okay. Yeah.
Yeah.
All right. Let's add stuff. So I got here. Let's do 1.5 I1 minus 2.5 equals 8 minus 0.4 I again. Then I'm going to move this guy over, but it's negative, so it goes over here, it becomes positive. So I get 1.9 I1, yeah? And then I'm going to move this over to this side, and I'm going to get what?
10.5.
10.5. Okay? Look it! The end is in sight. Can I solve for I1?
Yeah.
Yes, I can divide 10.5 by 1.9, and I get 5.526 amps. And then we put a smiley face, because we have one of 3 answers. Okay? I have one of my currents. So, now what are we going to do? I can go back to our friend up here. And I can say, hey, remember I2 equals I1 over 2 minus 5 over 2? All right? I'll make that nicer. Then can't I say, hey, I know I1. Boop. It's sound effects, make it happen, man. All right, so I'm going to take that and put it there, 5.526 over 2 minus 5 over 2. All right, and we can get it, look, real numbers. And so we can turn it 0.263 amps. Boop, 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 boop. Now, yep.
Last one. Okay.
Is there something wrong?
No, I don't.
I'm scared.
Let me check. Okay. wait.
Check. We thought not anything be wrong. My world will end. Okay,
Yeah. No, I don't know what I did in my head.
that's okay. This is like every little thing that.
I'm just talking to Julia.
Okay. All right. So now, how would you like to do the last one?
Oh.
Just add the 2 numbers together.
So we could do trashy stuff, and I think so we could take this horrible. We could take 5. Right, we could, we could just take this, right? We could say I3 equals 8 minus 2/5 I1 and put 5.526 here. And you know what you're going to get? People will know. 5.789 amps. And so you could do that, or you can, hello, I3 is I1 plus I2. Whoop, whoop, I3. And guess what you get? 5.789 amps. All right, that's one problem. No big deal.
Big deal.
No big deal. And it's all good when you got all the signs right. if one of those equations has a wrong sign, or you did some silly multiplication, right, it all goes bad. So, yeah, that's it. Okay, so now you just practice. And some are easy and some are harder, and you get more lost, and maybe you get found.
In the pursuit of